Hello and welcome to our video about the Taylor polynomial error. First, I'm going to review the Taylor polynomial itself. We defined in class that the nth degree Taylor polynomial for f of x centered at x equals c can be constructed using this formula and the values of f and its derivatives at x equals c. We use Taylor polynomials like this to approximate the value of the generating function. So if we wanted to approximate the value of f of a for some x value a, we would take a Taylor polynomial of degree n and plug in a, keeping in mind that that's only going to be a good approximation if a is near the center c. If you're far enough away from the center, this approximation becomes meaningless. But such an approximation is always going to have an error, and we're almost always interested in the absolute error. We can define the absolute error as the absolute value of the difference in the exact value of f of a and the Taylor polynomial approximation for that value. Taylor's theorem says that this error is always equal to the value of the n plus first derivative. Notice that we're using the nth degree Taylor polynomial, and so this is the n plus first derivative, evaluated at some value u divided by n plus 1 factorial times a minus c to the n plus 1. Absolute values here are meant to indicate that we're talking about the absolute error to make our formula a little bit easier to deal with. So a couple of things I want you to notice. First of all, this formula for the error looks identical to the formula for the nth term. We're just looking at the n plus first term. So n plus first derivative, n plus 1 factorial, n plus 1 power. A minus c corresponds to x minus c because we're evaluating the polynomial at x equals a, and so a goes in place of x. Now, we need a little explanation about this u. It is an x value, but the formula, his theorem says that this error, this is true, this equals the error for some u between a and c. So for some x value u between the center c and where we're evaluating the polynomial, that the error is equal to exactly this if we plug in that value of x. The problem is that in practice, finding the u where we have the exact error is very, very difficult, if not impossible in some cases. So what we do is we go and take some help from Lagrange. The Lagrange error bound says that we can find an upper bound for this error, which is usually all we need. So we've got our absolute error here. Lagrange says that that's less than or equal to m. I'll talk a little bit more about what m is in a moment, divided by n plus 1 factorial times the absolute value of a minus c to the n plus first power. So notice again, this looks very much like the Taylor's formula for the error, which is very much like the n plus first term of the Taylor polynomial. The absolute values here have moved are only around the a minus c because that's the only quantity in this formula that could possibly be negative. All right, we got to deal with that m. Well, we know it's got to have something to do with the n plus first derivative because it's what's replacing that in the previous formula. M is defined to be the maximum value or the maximum absolute value of the n plus first derivative for all x between a and c. So maximum absolute value of the n plus first derivative of x when we look at all the x's between a and c. That's replacing the actual value of the nth derivative at u, and it should make sense here that if we find the largest possible value of the n plus first derivative on this interval, we can then find an upper bound for this actual value, which is generally going to be sufficient. Okay, so what I want to do now is point you to a handout that is shared in Google Classroom. It's called the Commonly Used Taylor Series handout. I'm going to share my screen now so that we can look at the handout for a moment together. This is a table that lists the commonly used Taylor series, or if you chop them off, Taylor polynomials, that are seen. They're the ones that we see most frequently in our calculus courses. Now, some of these we've seen before, e to the x, cosine x, sine x, but look, conveniently, this is the one that we're going to need in the next example. This says that the natural log of the function 1 plus x is equal to x minus x squared plus x cubed minus x to the fourth over 4 plus x to the fifth over fifth, and so on, and is conveniently can be represented as a alternating series with general term x to the n divided by n. However, this is only true for x values near the center, and here near the center means x must be between -1 and 1, where +1 is included and -1 is not. So we're going to use this formula in our next example. So let's first make a note of that formula on our papers. That formula said that the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus, and I'll just go ahead and cut it off there, so on and so forth. And that is true if x is between -1 and 1. Okay, so example 7 from our lesson in class. We didn't get to this one, so I wanted to make sure I included it in the video. We want to find the second degree Taylor polynomial for f of x equals natural log of 1 plus x, centered at x equals 0. I want to point out that the formulas on the commonly used Taylor series handout are all Maclaurin series, so they only work when our center is 0. Well, based upon our formula here, if we want P2, the second degree approximation, P2 of x would just be x minus x squared divided by 2, just the first two terms up to the second degree, which we can then use to approximate the natural log of 1.25. Well, notice that that is the natural log of 1 plus 0.25. That puts it in the form for which our f of x can be used. Natural log of 1 plus x, so 1.25 is 1 plus 0.25. So we're going to approximate that with P2 of 0.25. That's the x value that we'd be plugging in to the natural log of 1 plus x. Well, P2, we're plugging in 0.25 into x minus x squared over 2. Well, 0.25 is 1/4. So it'd be 1/4 minus 1/4 squared over 2, which is 1/4 minus 1/64, or 15/64. And it's very often useful to have a decimal approximation. So in this case, 0.234375. And actually, that's not an approximation. That is actually the actual value of 15/64. So we have used the second degree Taylor polynomial to approximate the natural log of 1.25, and we've come up with this decimal approximation. Now, anytime we do an approximation, we're going to be interested in how far off is this? What is the error? So in part C, we're going to use the Lagrange error bound to find the largest possible error in our approximation from part B. Well, our error is the natural log of 1.25 minus our second degree approximation. The Lagrange formula said that this error is less than or equal to m, we'll come back to that in a moment, divided by, well, this is the n plus 1 factorial. Well, n is 2, second degree, so this is 3 factorial. times our 0.25 minus the center, which is 0, quantity cubed. The quantity 0.25 minus 0 is positive, so the absolute values don't end up doing anything here. Well, now we got to come back to our m. We defined m to be the maximum value, or the maximum absolute value of, in this case, it would be the third derivative, right? 3 is degree 3, so we got our third derivative here, of third derivative of x on the interval between a and c. In this case, a is 0.25 and c is 0, and so I'm going to represent that using the closed interval 0, comma 0.25. And I'll just write that underneath the max so it can kind of hold on to it there. Well, I did some work. We need the formula for the third derivative. I did some scratch work here before the video. F of x is the natural log of 1 plus x, so f prime is 1 over 1 plus x, so f double prime is negative 1 over 1 plus x squared, and f triple prime would then be positive 2 over 1 plus x cubed. So this is the formula we need. So we need to know the maximum absolute value of 2 divided by 1 plus x cubed on the interval 0 to 0.25. Now, for positive values of x, the 1 plus x cubed is going to be positive. And so again, here the absolute values don't really impact us very much, or don't impact us at all. So we can actually just go ahead and say, oh, we're just talking about that maximum of that function. Now, to find this maximum, we could do an optimization procedure from calculus AB, but it's simpler than that. We just simply need to recognize that 2 divided by 1 plus x cubed is a transformation of y equals 1 over x to the n for n bigger than or equal to 1, right? N here would be 3 in our situation. And now the 2 multiplying by 2 is just a vertical stretch, and adding the 1 is just a horizontal shift. So that means the general shape of this function is going to be the same as the general shape of this function. Well, 1 over x to the n for n greater than or equal to 1 is our basic rational graph. Notice that it's always decreasing. That's what we needed to know, because on the interval from 0.20 to 0.25, this value, 2 over 1 plus x cubed, will also always be decreasing. Well, if a function is decreasing, its max is going to be at the leftmost endpoint. So our max here is going to be at x equals 0. So we're going to evaluate the function, the third derivative, at x equals 0. And, well, 1 plus 0 cubed is 1, so this is 2. So our m for the Lagrange error bound is 2. Well, let's go back up here and plug that in. So 2 over 3 factorial, 0.25 cubed. Okay, I'm going to write that as 1/4 cubed. Well, doing some arithmetic here. 3 factorial is 6, so 2 over 6 is 1/3. 1 over 4 cubed is 1/64. Then 3 times 64 is 192. And so that means that our Lagrange error bound is approximately 0.005208. So that means the error in our approximation from part B for the natural log of 1.25 is only off by at most a little bit more than 5/1000ths, which is a pretty tight bound. So that means we've at least got the first 2 decimal places correct, and we might even have the third correct, depending on the actual size of the error. Okay, so that's how we apply the Lagrange error bound. The actual error, or the absolute error, is always going to be bounded above by the maximum of the n plus first derivative divided by n plus 1 factorial times a absolute value of a minus c to the n plus first term. So we're using all the n plus 1 things over here on the right because we're using the nth degree polynomial in the actual error. Okay, so that finishes example 7. What I'd like for you, well, no, that actually does not finish example 7. We got one more part to do. But what I want you to do right now is to pause the video and go back and review the formulas and work back through parts A, B, and C of example 7 to be sure that you understand what we've done and haven't missed any details. So rewatch the video if you need, or just think back through your notes. Okay, so I'm assuming you took a little break to review. And now we're going to do part D of example 7. We want to know for what values of n does the nth degree polynomial, Taylor polynomial, evaluated at 0.25, approximate the natural log of 1.25 with an error of less than 1/1000th. So if we want to tighten up our bound so that the error is no bigger than 1/1000th, what value of n, meaning what degree polynomial, do we need to use to approximate the natural log? Well, this is a statement about error. So our error, again, as we've seen, absolute value of natural log 1.25 minus the nth degree polynomial evaluated at 0.25. Again, so the change here is we're not looking at a specific degree like 2 in the previous part of the problem. We're looking at the nth degree, the general degree Taylor polynomial. Well, we're still going to use Lagrange here. Same formula as before. M divided by n plus 1 factorial times the center 0.25, or excuse me, the A where we're evaluating minus the center 0 raised to the n plus 1 power. Well, again, n is the issue, or m rather, m is the issue because we're solving for n. That's okay, we've got that in there, but we need to figure out what m is equal to. Now, if you recall, m is the maximum. In this case, it's on the interval from 0 to 0.25, right? From the center to where we're evaluating, the absolute value of, this is the nth polynomial. So again, I need the n plus first derivative. Now we already know, excuse me, well, here's what we don't know. We don't have a formula for the n plus first derivative. So we've got to do a little work to find that formula. So here's what we're going to do. We're going to go to the side and do some scratch work for a moment. We need a formula, a generalized formula for the n plus first derivative of the natural log of 1 plus x. So on a previous page, we had looked at the first 3 derivatives, right? We got up to that point right there, and that's just repeated application of the power rule. But we don't see a pattern yet. So let's find a few more derivatives and see if we can find a pattern. It will be helpful. Let's rewrite this as just a power function. So 2 times 1 plus x to the negative 3 power. So when we want the fourth derivative, negative 3 times 2, or negative 2 times 3, that's the same thing, raised times 1 plus x to the negative 4th power, which would then be divided by 1 plus x to the 4th power. 1 plus x quantity to the 4th power. All right, so if we take the derivative again, it's going to be the same kind of pattern. Negative 4 times negative 2 times 3, which I will write as positive 2 times 3 times 4. The negatives cancel. Divided by, okay, the power here would drop down to negative 5, so this would be 1 plus x to the 5th power. All right, I want you to pause the video for just a second and see if you can recognize the pattern that has developed here. Can you give me a formula for the nth derivative of x based upon this sequence of derivatives? All right, so you pause the video. You tried to find that formula for yourself. If you didn't, go back and do it now. All right, so let's see here. The numerator in this formula looks very much like a factorial. In fact, it is. This is 4 factorial. Well, 4 factorial is in the 5th derivative. So the numerator of this calculation is always n minus 1 factorial. All right, the factorial begins at a value exactly 1 less than the order of the derivative. And the denominator is always 1 plus x raised to a power, and that power is always equal to the degree or the order of the derivative. So that in this case, this would be 1 plus x to the nth power. So we have the formula for the nth derivative of f of x equals natural log of 1 plus x. On the previous page, we needed the formula for the n plus first derivative. So all we need to do here is replace the n's with n plus 1. So this would be n plus 1 minus 1 factorial over 1 plus x to the n plus 1. Now, I just noticed that we missed something. Our derivatives here, positive, negative, positive, negative, positive, they're alternating. So we need to multiply our formula here by an alternating factor. Well, we know how to do that. That's going to be a power of -1. So let's squeeze that in right there. Well, just got to figure out what power it's going to be. When the order of the derivative is odd, we get a positive value. When the order of the derivative is even, we get a negative value. So we can't use -1 to the n because that would give us positive and positive, negative and negative. We need them to be off. So what I'm going to do here is I'm going to raise that to the n minus first power. That way that an even n gives a positive value and an odd n gives a an even n gives a negative value and an odd n gives a positive value. I chose n minus 1 rather than n plus 1 just because I already had an n plus 1 in my formula. And then down here, we'll squeeze that in as well. -1, well, that would be n plus 1 minus 1. All right, so we're replacing all the n's with n plus 1s. Okay, well, that's kind of ugly. Let's see if we can clean it up. -1, n plus 1 minus 1 is n. N plus 1 minus 1, again, is just n. So n factorial over 1 plus x to the n plus first. So can't simplify the denominator anymore. So this is our formula for the n plus first derivative that we needed on the previous page. So let's go back and use that formula. So m is the maximum of the n plus first derivative. So, and we just determined that the formula for the n plus first derivative is -1 to the nth power times n factorial over 1 plus x to the n plus first power. Now you can see why we need the absolute values, because now it kills the alternating part, the -1 to the n. So we're just looking at the maximum absolute value of n factorial over 1 plus x to the n plus first. Still looking at the interval from 0 to 0.25. All right, now this maximum here, we can use the same logic as before. For a particular value of n factorial is a constant, and n plus 1 is going to be a power bigger than 0. Or bigger than 1. So we're still dealing with a transformation of 1 over x to the n when n is bigger than or equal to 1, and you remember for the last page that is always going to be decreasing for positive x values. So we know that this maximum occurs at the smallest possible value of x. So we just plug in x equals 0. 1 plus 0 is 0. So we just get n factorial when we plug in x equals 0. All right, that's what we needed in our error bound calculation. So what I'm going to do is I'm going to copy that formula down for our error bound. All right, so the error, natural log of 1.25 minus the nth degree polynomial evaluated at 0.25 is less than or equal to, all right, our m we now know is n factorial divided by n plus 1 factorial. All right, just copying our formula from above. And the 0.25 minus 0 to the n plus first power, okay, I'm just going to write that as 1/4 to the n plus 1 power. Well, that can be simplified. We know that when we have a quotient of factorials, the n factorial and in the numerator cancels with the n factorial in the denominator, just leaving us 1 over n plus 1. And I can write the 1/4 to the n plus 1 as 1 over 4 to the power n plus 1. It's going to make calculations a little bit easier. Now, we want this error, right? The problem said, let's go back up to the top here. How many terms do we need to ensure that the error is less than 1/1000th. So we need this error formula to be less than 1/1000th. So we've got a little equation here to solve. Now, we're not going to solve this algebraically, although in this case we very much could. You can do some algebra and solve this, or you might be able to. It's kind of a difficult inequality to solve, but we can just test it by inspection. We can just kind of guess and check. We know that n equals 2 terms is not enough. We showed that in part C. So let's test n equals 3 and see if our error is small enough. Well, for n equals 3, 1 plus n plus 1 over n plus 1 would be 1/4 times 1 over 4. Again, n plus 1 is 4. Well, that's 1 over 4 to the 5th power, which is 1 over 256. Notice that 1 over 256 is still bigger than 0.001, the value of 1/1000th. So that means when n is 3, our error could be as large as 1 over 256, which is still too big. It's bigger than the error required. So let's check n equals 4. Okay, that would be 1 over 5 factorial times 1 over 4 to the 5th. It's not 5 factorial, it's just 5. 1/5 times 1 over 4 to the 5th. Well, that's 1/5. We already know what 4 to the 5th is. That's 1 over 256. Hey, looks like we got a winner here. 5 times 256 is 1,280. So since 1,280 is bigger than 1,000, this fraction is less than 1/1000th. All right, so now we know. So the largest possible size of the error when using the 4th degree Taylor polynomial is 1 over 1,280, which is less than 1/1000th as required. So that's the one check. That's the one we're looking for. So our answer here would be we need the 4th degree polynomial. All right, 4th degree Taylor polynomial to approximate the natural log of 1.25 with an error of less than 0.001. Okay. So once again, I want you to pause the video, rewind, and go back through part D of this example and make sure you can follow the logic. So just to summarize, we wanted to find the value of n for which the nth degree Taylor polynomial approximated the natural log of 1.25 with an error of less than 0.001. So we set up our equation for the error, and we know by Lagrange that it's less than or equal to this formula. Well, we needed to know the value of m, so that's the maximum of the n plus first derivative. We went over to the next page, came up with the formula for the n plus first derivative, and then recognized that it is a decreasing function, so its maximum must be at x equals 0. Plugging in x equals 0, we got n factorial. Putting that back into our Lagrange error bound gave us a formula in terms of n that we want to be less than 1/1000th. This is our upper bound for the error. We want that upper bound for the error to be less than 1/1000th according to the problem. We did a little guess and check here and showed that for n equals 4, that error bound is less than 1/1000th. So we need the 4th degree Taylor polynomial. So pause the video, go back and review this part of the example, and make sure that you understand what we've done. Okay, so that is the end of example 7 as it was written in our lesson. But I want to go back and make a comment here that's actually very, very important in terms of quiz and test problems. Example 7 specified that we use Lagrange. It said use the Lagrange error bound. However, the Taylor series for natural log of 1 plus x is alternating, and it's convergent if x is in the interval from -1 to 1. Well, our x equals 0.25 is in that interval, so we have a convergent alternating series. Okay, so our x equals 0.25 is in this range, so we have a convergent alternating series, which means we can use the alternating series error bound, which is much simpler and actually a better estimate of the error, a tighter estimate of the error. So if we're using, if we go back to part C, the second degree approximation, the alternating series error bound says that the error has to be less than or equal to the size of the first neglected term. Well, the size of the first neglected term would be the size of the first neglected term is x cubed over 3. So this is less than or equal to 0.25 cubed over 3 factorial. I'm using 0.25 here for x because that's where we're evaluating the polynomial. Well, that would be 1/4 cubed over 3 factorial. Okay, it comes out to be about 0.002604. This error bound is smaller than the error bound we found with Lagrange. It's a tighter error bound. Okay, so that means our approximation from 7b is actually better than Lagrange said it was. In part D, we could also have used the alternating series error bound and made the problem much easier. We're using the nth degree Taylor polynomial here. So the alternating series error bound says the error is no bigger than 0.25 to the n plus 1 power divided by n plus 1 factorial. And that's the quantity that we need to be less than 1/1000th. So we're going to use the same method as before. We got a much simpler formula, and I didn't have to find that n plus first derivative. I was able to come straight here just by looking at the third degree term of the polynomial. Well, okay, so we test it for n equals 2. Excuse me. For n equals 2, I'm just going to repeat this case. We know this is not the answer, but I just want to show how we can rule it out. The exponents, the n plus 1, n plus 1, those would be 3s. So that's 1 over 384, which is still bigger than 1/1000th. So we know that the second degree polynomial is still not enough. Well, let's look at n equals 3. That would be 0.25 to the 4th power over 4 factorial, which is equal to 1 over 6,144, which is less than 1/1000th. Okay, as required. So the Lagrange error bound said we needed at least 4 terms. We needed at least the 4th degree polynomial, but the alternating series bound gets us a tighter bound, right? The error bound is always going to be smaller than the Lagrange error bound. So that means in that case, it's tight enough that we actually can prove that we only need 3 terms to have an error of less than or equal to 1/1000th. So keep in mind that the alternating series error bound is a tool, and on a quiz or a test on the AP exam, when you recognize that you have an alternating convergent series, then you should use the alternating series error bound in these type of problems. Don't try to use Lagrange when it's not required or necessary that you use Lagrange. All right, that's the end of our video. I'm going to post these notes on Google Classroom and the link and and the handout of the commonly used Taylor series. I hope this was helpful. Y'all have a great asynchronous Wednesday.